Steel rods move through a 1,750 degrees Fahrenheit walking beam furnace, where controlled heating ensures uniformity. Automated transport maintains consistency, while precision temperature control optimizes the coiling process. Surface mining machines cut raw material precisely, eliminating drilling and blasting. The cutting drum breaks rock to the required size, while conveyors transport it efficiently. Adjustable slopes optimize drainage, ensuring drier material. The selective mining process improves resource utilization, minimizing waste. Stable haul roads support truck transport, reducing operational costs. The continuous cutting and loading system maximizes output, maintaining uniform material quality with lower environmental impact. At Mayada plant, precision engineering shapes the Lexus NX, integrating turbocharged and hybrid systems through advanced manufacturing techniques. Over 8 weeks, specialists rewound the 15 MVA Elin generator rotor, individually installing and insulating 300 copper turns before high-speed balancing to eliminate vibrations and ensure precision. Rotational molding begins with cleaning the mold and applying a graphic logo. Metal inserts are placed before adding polyethylene powder. The mold rotates inside an oven, evenly distributing the melted plastic. After the first layer forms, a foaming polyethylene layer is added for strength without excess weight. A final layer seals the interior. Cooling allows crystallization, ensuring durability. The mold is opened, revealing the formed boat, which undergoes quality checks, thickness measurements, and final trimming. Post-production fittings are installed before shrink wrapping for protection. The finished boats are stored and prepared for delivery. At Servi Group's Kongsberg facility, hydraulic valve production starts with precision machining of nodular cast iron, stainless steel, and aluminum. 4 automated machining centers, integrated into a flexible manufacturing system, utilize over 1,000 tools to create complex cavities in hydraulic manifolds. Each cavity undergoes measurement and inspection to meet exacting specifications. Next, thermal deburring removes residual metal shavings using a methane-oxygen explosion exceeding 1,300 degrees Celsius, ensuring clean internal channels. The components then receive in-house surface treatment before final functional and pressure testing, simulating real operating conditions to detect any defects. At the Lissa facility, hydraulic cylinders are manufactured using CNC machining and submerged arc welding, forming high-strength joints for large tubes. Hardened spools are ground to micrometer precision for flawless operation. Each cylinder undergoes pressure testing, cleanliness control, and particle analysis to meet offshore and industrial standards, guaranteeing durability in extreme environments. At Geerks Marienhütte, steel production starts with melting sorted scrap metal in a direct current electric arc furnace. The molten steel undergoes refining to remove impurities before continuous casting, where 6 strands move in sync to prevent cracks. Precision rolling mills shape the steel to exact tolerances. Alloying elements like manganese and chromium enhance strength. Finally, surface treatments refine texture, ensuring high durability for industrial applications. Aqua Group's manufacturing process starts in the in-house foundry, where gray iron, non-ferrous alloys, and stainless steel are melted in induction furnaces at precisely regulated temperatures. The molten metal undergoes spectrometric analysis to verify its chemical composition. identifying and eliminating impurities before casting. The liquid metal is then poured into preheated high-precision sand molds, designed to maintain dimensional accuracy and reduce defects like porosity. To ensure uniform solidification, the molds are carefully engineered for controlled cooling. Once solidified, castings are removed and subjected to a gradual cooling process, minimizing thermal stress and preventing microscopic cracks that could weaken structural integrity. Cold wound springs undergo controlled heating in stress relief ovens, reducing internal stress and enhancing structural integrity. This documentary details the precise manufacturing of an 8.5 megawatts Francis turbine stay ring. The process involves heavy fabrication, welding, precise machining, and rigorous quality inspections. Advanced CNC technology ensures exact specifications, while skilled engineers oversee every stage. This crucial component is crafted for durability, efficiency, and optimal performance in hydroelectric turbines. The roller casting process in Siegerland has a long tradition dating back to the 19th century, with a strong emphasis on precision and durability. The process begins with mold preparation, a critical step that determines the quality of the final product. Each roller requires a custom-built mold, typically consisting of a lower mold box that supports the weight of the form and molten metal. Skilled craftsmen carefully assemble and align the mold components, ensuring structural integrity and accurate dimensions. Once the mold is ready, the metal preparation phase begins. High-quality raw materials, including iron and steel alloys, are melted in specialized furnaces, such as cupola or electric arc furnaces. Various alloying elements are added to achieve the desired hardness and wear resistance. Before pouring, metallurgical tests are conducted to verify the composition and temperature of the molten metal. Slag removal ensures a clean melt, enhancing the quality of the final casting. The actual casting process employs the static stand casting method. In this technique, molten metal is poured into the mold from the bottom upwards through tangential inlets. This controlled filling method prevents turbulence and ensures a uniform distribution of the metal, minimizing defects such as porosity or inclusions. The metal gradually fills the mold, solidifying in a way that enhances the roller's mechanical properties. After solidification, the roller undergoes controlled cooling to prevent internal stresses and cracks. The mold is then dismantled, and the raw casting is extracted. At this stage, excess material, such as gating systems and risers, is removed. The rough casting is subjected to heat treatment, including annealing and tempering, to refine its microstructure and achieve optimal mechanical performance. Machining is the final phase, where the roller blank is processed to its precise specifications. Specialized lathes and grinding machines are used to shape the roller, ensuring uniformity in diameter and surface finish. The final product undergoes rigorous quality inspections, including hardness testing, ultrasonic analysis, and dimensional checks. These procedures guarantee that the roller meets stringent industry standards for durability and performance. Despite technological advancements, many fundamental aspects of roller casting in Siegerland remain unchanged. The combination of traditional craftsmanship and modern engineering continues to produce high-quality rollers, reinforcing the region's reputation as a key player in European roller manufacturing. Mooring ropes are secured by tightly braiding the ends, then splicing strands together for strength. Whipping with heavy-duty thread prevents fraying. Seizing wire or resin is applied to lock fibers in place. Knots are carefully tightened to distribute force evenly, ensuring stability and preventing failures under extreme loads. Stainless steel tank production begins with laser cutting AISI 304 and 316 L sheets to exact dimensions, ensuring precision in every component. Conical bottoms, up to 5,000 millimeters in diameter, are formed using hydraulic presses for uniform shaping. Automated TIG welding with controlled parameters creates seamless joints, followed by multi-stage grinding and polishing to achieve a surface roughness of 0.8 micrometers raw. Tanks undergo rigorous hydrostatic pressure and helium leak tests to verify structural integrity. For sterile applications, orbital welding with inert gas shielding eliminates oxidation, while internal surfaces receive electropolishing to enhance cleanliness and corrosion resistance. Finally, heating systems, either steam or electric, are integrated based on specific process requirements. Steel production at Altoros de Mexico follows a fully integrated process, starting from raw materials and ending with finished steel products. Iron ore from the mines undergoes pelletization, where it is filtered, mixed with binding agents, and hardened at 1,300 degrees Celsius. Meanwhile, metallurgical coal is transformed into coke through an 18-hour baking process, providing the essential fuel for blast furnaces. In these towering furnaces, raw materials, iron ore, limestone, dolomite, and coke are layered and subjected to temperatures of 1,650 degrees Celsius, reducing iron oxides into molten pig iron. This pig iron is then refined using either a basic oxygen furnace or an electric arc furnace, where high-pressure oxygen and electrical energy purify and convert it into liquid steel. The molten steel is cast into slabs through continuous casting, then processed in hot and cold rolling mills to achieve precise thickness and mechanical properties. Additional treatments, including annealing, skin pass rolling, and tension leveling, enhance uniformity and surface quality. To improve durability, steel may undergo tin plating or tin-free coating. The process begins with heating metal billets to forging temperature. Electrohydraulic controls position each piece under steam hammers, 300 kilogram to 6,000 kilogram, or hydraulic presses. Repeated hammering shapes the metal precisely, refining its grain structure. Forgings weighing 50 kilograms to 2,500 kilograms are continuously monitored to ensure dimensional accuracy and material integrity. The AIM 4000 Six-Axis CNC Coiler is an advanced machine designed to enhance productivity by increasing run rates and reducing setup time. Featuring 6 servo-controlled axes and single-point coiling technology, it efficiently produces compression springs, torsion springs, and wire forms with high precision, eliminating the need for mechanical adjustments. Line with a cut-to-length shear efficiently processes coil material into precise blanks. The operation begins by threading high-strength material into the system. The initial coil section is trimmed to create a smooth leading edge. Next, The coil sheet undergoes homogenization to ensure material consistency. A 17-roller straightener corrects any strip curvature, optimizing flatness. Loop adjustment follows to regulate tension and alignment. The material is then accurately cut using a 4-column swiveling shear for straight-edge blanking. Finally, the blanks are automatically stacked for streamlined handling. With high-speed capability, reaching up to 110 strokes per minute, the system ensures precision, efficiency, and high production output. The production of steel valve components begins with the lost wax casting process, which ensures precision and efficiency. Initially, wax patterns are injected into molds, forming solid replicas of each component. These patterns are cleaned, marked with heat numbers for traceability, and assembled with gates and risers to control metal flow. The wax patterns are then coated in multiple layers of refractory material, with immersion in binders for 20 minutes per layer to strengthen the shell. Once the shell hardens, the dewaxing process melts and removes the wax, leaving a hollow mold. The molds are then fired in furnaces at 800 degrees Celsius for 2 hours to enhance durability and eliminate residual wax. The molten metal is poured into the molds, maintaining strict chemical composition standards verified through spectrometer analysis. For sand casting, a cope and drag mold system is used, particularly for larger diameter valves, requiring more metal. A wooden pattern is placed in a sand-filled box, compacted, and treated with carbon dioxide to solidify the mold. Once metal is poured and cooled, the shells are broken, excess material is removed, and parts undergo heat treatment. Final steps include grinding, X-ray inspection, machining, and assembly. Valves are tested for pressure resistance before being painted and stored for shipment. This method ensures high-quality, durable valve components for industrial use. The production process at clay valve begins. Clay valve production process begins with precise engineering, where technical requirements are transformed into functional designs. Engineers utilize advanced 3D modeling and rapid prototyping to test and evaluate new products in specialized laboratories. Next, the casting process takes place. Intricate patterns are created to form sand molds, into which molten metal is poured to produce cast components. These alloy-based castings undergo rigorous testing to ensure strength and compliance with technical standards. Once cast, the components are machined using CNC equipment to achieve high precision. After machining, surfaces are treated and coated for corrosion resistance, ensuring long-term durability. Assembly is carried out by skilled technicians, including the installation and testing of pilot controls before integrating them into the final valve assembly. Finally, every product undergoes strict quality control procedures, including pressure testing, before being packaged and shipped. Spring production involves two main methods: winding and coiling. Winding shapes pre-tempered steel wire up to 26 millimeters using CNC machines, ensuring precise dimensions. Coiling, used for thicker wires up to 55 millimeters, wraps the material around a mandrel before undergoing heat treatment. Cold forming is suitable for wires up to 32 millimeters in diameter, After shaping, springs go through stress relief, grinding, and deburring to refine their structure. Shot peening enhances durability by strengthening the surface, while protective epoxy or polyester coatings prevent corrosion. Each spring undergoes rigorous testing before mass production. Focal speaker manufacturing process at its Saint-Étienne factory involves advanced machinery and meticulous craftsmanship. The production of speaker diaphragms, starting with precision CNC cutting to shape the raw materials. These diaphragms then undergo a specialized coating process to enhance acoustic performance. Automated robotic arms assist in assembling the voice coils and magnets, ensuring precise alignment. Once completed, every speaker unit undergoes rigorous acoustic testing in an anechoic chamber, where frequency response and distortion levels are analyzed. A laser measurement system checks the accuracy of each component before final assembly. This integration of high-tech automation and expert craftsmanship ensures focal speakers deliver superior sound quality. The GE Slitting Line 1300 is a high-performance system engineered to slit metal coils into narrower strips, optimizing material utilization in subsequent manufacturing processes. It accommodates coils weighing up to 40,000 kilograms and widths up to 2,800 millimeters, handling thicknesses between 0.08 and 12.0 millimeters. The process begins by loading a master coil onto the uncoiler. The metal strip is then fed through the slitter, where rotary knives make precise longitudinal cuts, producing strips of desired widths. These strips are subsequently rewound into coils by the recoiler, ready for downstream applications. Additionally, the line is designed to handle material strengths exceeding 1,800 N per square millimeter and yield points up to 1,200 N per square millimeter, ensuring versatility across various metal types. It begins with wax injection, where a wax model is created. Then, shell building forms a ceramic coating around the model. In dewaxing, the wax is melted, leaving a hollow ceramic mold. Casting follows, with molten metal poured into the mold. After shell removal, the solid metal valve is exposed. Heat treatment strengthens the material, while machining ensures accuracy in size and finish. Finally, the components undergo assembly and rigorous testing to guarantee performance. Investment casting, or the lost wax process, is a precise manufacturing method used for creating complex metal components. It begins with the production of a wax pattern, typically made using injection molding or 3D printing. These wax patterns are assembled into a tree-like structure and coated with ceramic slurry and fine sand to create a durable mold. Once the ceramic shell is fully dried, the wax inside is melted and removed, leaving a hollow mold. The mold is then preheated before molten metal is poured in. After the metal solidifies, the ceramic shell is broken away, revealing the raw casting. The individual castings are then cut from the sprue and undergo finishing processes such as grinding, machining, and polishing. This process produces high-precision parts with fine details, thin walls, and excellent surface finishes, reducing or eliminating the need for machining. Investment casting is widely used in aerospace, automotive, and medical industries due to its ability to create intricate and high-strength components. The manufacturing process of PED's coil springs begins with high-quality, high-grade steel cut to precise lengths. The steel is then uniformly heated to 900 degrees Celsius in a gas-fired walking beam furnace, ensuring consistent material properties. After heating, the steel is shaped into coils using a CNC winding machine. The hot wound coils are then quenched in an oil bath for rapid cooling before undergoing tempering in a gas-fired furnace to enhance elasticity and durability. Next, the coils are ground for flat ends if required, followed by shot peening, where steel beads remove impurities and relieve stress. Afterward, each spring undergoes rigorous testing, including scragging and load height verification. Once approved, the springs are powder-coated using an electrostatic process and cured at 220 degrees Celsius. Finally, the finished coils are cooled, packed, and prepared for distribution, ensuring high standards and reliability. The powder coating process begins with pre-treatment, including a 5-stage iron phosphate rinse, deionized baths, and sealing. After drying, electrostatically charged powder is applied before curing. The Yamada HG-1003 digital hybrid hydraulic press integrates an advanced automatic tool changer, ATC, streamlining tool setup and angle accuracy adjustments. Designed for high mix, small batch production, this next-generation system automates tool changes, reducing manual intervention and increasing efficiency. The hybrid hydraulic design enhances precision and adaptability, ensuring consistent performance across multiple part types. By optimizing automation, the press brake improves workflow, minimizes downtime, and meets the evolving demands of modern manufacturing. Cold winding and hot winding are two distinct spring manufacturing processes. Cold winding uses high-tensile chrome silicon for lightweight, high-deflection springs, while hot winding forms larger springs by heating bars to 1,750 degrees Fahrenheit before coiling, quenching, and tempering. In cold coiling, wire moves through rollers and fulcrum pins, wrapping around a fixed mandrel to form coils. Aircraft tire production begins with precise layering of rubber, nylon, and steel belts for strength. High-pressure molding shapes the structure, then vulcanization bonds materials under controlled heat. Laser scanners detect microscopic flaws, ensuring uniformity. Computerized systems fine-tune weight distribution, preventing imbalances that could affect high-speed performance. The truck unloads wheat into the receiving pit, where conveyors and bucket elevators transport to silos for storage and processing. The machine molds 18 hollow or solid blocks, 20 by 40 by 20 centimeters per press, and 42 linked blocks per cycle. Raw materials, including cement, sand, and aggregates, are fed into the hopper, then evenly distributed into the mold cavity. A hydraulic press applies high pressure to compact the mixture, ensuring uniform density. The freshly formed blocks are transferred onto 140 by 130 centimeters pallets and manually transported using a hand trolley. A lift and lowering device carefully stacks the pallets for the curing process, allowing blocks to gain strength. The maintenance chamber ensures smooth operation. The PLC system precisely controls material feeding, compaction, and curing, guaranteeing consistent block quality and dimensional accuracy. The installation begins with site excavation to create a stable foundation. A bedding layer is compacted before precast concrete sections are precisely lowered into place. Workers align and seal the joints, ensuring structural integrity. Backfilling follows in layers, with compaction at each stage to prevent settling. Finally, the surface is restored for proper load distribution. Crews install a 28-foot span, 9-foot rise con/span B series on Bacon's Bridge Road, aligning precast sections and securing joints for structural stability. Each Kursk beam, measuring 40 meters and weighing 52 tons, was carefully aligned and positioned. The regenerator vessel's top section, housing cyclones, was cut free using a precision milling machine that gradually penetrated its 32 millimeters thick steel wall. Custom-engineered rigging was designed and securely attached to stabilize and lift the massive structure. The new 481-ton regenerator head was transported along a designated route to the skid bridge, where it was carefully maneuvered into place. The complex lifting process, lasting 2 hours, required absolute control to maintain alignment. The 14-meter diameter structure demanded a strict plus or minus 10 millimeters tolerance, achieved through advanced machining techniques. Exceptional precision ensured an extraordinary accuracy of just 1 millimeter, allowing seamless integration within the existing framework while maintaining structural stability. Soil cement is formed by blending Type D borrow, Portland cement, and water, then uniformly compacted to achieve 500 psi strength. On US 301, 6 inches of soil cement were placed, compacted in layers, and cured before adding 4 inches of permeable treated base, followed by 12-inch Portland cement concrete pavement. Vitubau specializes in road rehabilitation using on-site asphalt recycling technology. The process begins with assessing road conditions, cleaning the surface, and milling the old asphalt. The recycled material is mixed with new binders and additives, then evenly spread and compacted using specialized machinery. Quality checks ensure durability and adherence to safety standards. This eco-friendly method reduces costs, conserves resources, and minimizes environmental impact while maintaining road infrastructure efficiently. The construction of the 1915 Çanakkale Bridge, the longest suspension bridge in the world, with a main span of 2,023 meters, was a complex and meticulously planned engineering project. Work began in March 2017, requiring advanced construction techniques to overcome environmental and geographical challenges. The first phase focused on site preparation, including the establishment of 3 separate construction sites. A massive dry dock, 11.5 meters deep and capable of accommodating 1,800 cars, was built within 200 days. This facility played a crucial role in assembling and transporting bridge components. The foundation consisted of 2 enormous caissons, each weighing 80,000 tons, requiring 160,000 tons of steel and concrete. These structures were carefully positioned on the seabed to ensure stability. In the offshore construction zone, 357 steel piles, with diameters of 2.5 meters and lengths ranging from 21 to 46 meters, were driven into the seabed. Each pile, weighing between 35 and 65 tons, was installed over 200 days, overcoming challenges such as strong sea currents and high winds. Once the foundations were secured, 2 steel towers, each 318 meters high, were assembled to support the suspension cables. The final stage involved installing the main cables and assembling the bridge deck, ensuring precise alignment. To protect marine life, construction was paused whenever dolphins entered a 500-meter safety zone. Completed in 2022, the bridge significantly enhances transportation between Europe and Asia, marking a major milestone in Turkey's infrastructure development. The production of a large sweeping machine begins with frame fabrication using welded high-strength steel for durability. Next, the engine and hydraulic system are installed to power the brushes and suction unit. The brush and suction system is then mounted, followed by a water spraying system to control dust. Electronics and automation are integrated for optimal functionality. Finally, the machine undergoes rigorous testing to ensure efficiency and reliability before being released for industrial and municipal cleaning applications. The Ocean Railway Bridge was manufactured using a precision-engineered modular construction process. Steel components were laser-cut and welded in a controlled factory setting to ensure structural integrity. The concrete segments were precast using automated molding systems, allowing for consistency and strength. On-site, hydraulic lifting machines and gantry cranes positioned the bridge sections accurately. The alignment was verified with GPS-guided surveying equipment, ensuring precise placement. Finally, automated welding and bolting systems secured the components, and load testing machines verified structural stability before railway operations resumed. This high-tech approach minimized disruption and enhanced construction efficiency. Precision Pipeline, LLC PPL, employs advanced automation for efficient pipeline construction. The process starts with GPS and GIS-based route planning, followed by land clearing and trenching using excavators and trenchers. Automated welding machines join pipes, while corrosion-resistant coatings enhance durability. Hydraulic lifting systems and precision alignment tools ensure accurate placement. Finally, hydrostatic pressure tests, ultrasonic scans, and robotic crawlers inspect the pipeline for structural integrity. The production process of Rangeley Muddlehouse Vision is a highly efficient, precise, and sustainable modular construction method. By integrating digital design, automated manufacturing, and rapid on-site assembly, this approach significantly reduces waste, optimizes energy efficiency, and accelerates construction timelines. Digital planning and design. The process starts with Building Information Modeling, BIM, a digital tool that enables precise design, structural analysis, and resource optimization. This technology ensures that all components fit together perfectly while improving material efficiency and minimizing errors. BIM also allows for early integration of energy-efficient features, such as optimized insulation and passive solar design, which contribute to sustainable performance. Prefabrication in a controlled factory environment. Once the design is finalized, the prefabrication process begins in Rangeley's highly controlled factory setting, using CNC, computer numerical control technology. Wooden components are cut with extreme accuracy to ensure a perfect fit. These prefabricated elements are then assembled into modular units, incorporating high-performance insulation and triple-glazed windows to maximize thermal efficiency. To enhance quality and reduce construction time, all electrical wiring, plumbing, and mechanical systems, such as heating, ventilation, and cooling, are integrated within the modules during factory production. This method ensures greater precision and minimizes the need for extensive on-site installation work. Interior and exterior finishing. Following structural assembly, the modules undergo interior and exterior finishing. Inside, walls, ceilings, and flooring are completed, using high-quality, sustainable materials. The controlled factory conditions ensure that finishes are applied evenly and consistently. Exterior cladding is also installed, enhancing durability and aesthetic appeal while providing additional insulation and weather protection. Transportation and on-site assembly. Once fully constructed and quality checked, the completed modules are transported to the building site. Their modular design allows for easy transportation and minimal handling. On-site, the units are assembled using cranes, drastically reducing construction time compared to traditional methods. Since most work has already been completed in the factory, installation can be finished in just a few days, minimizing disruptions to the surrounding environment. Quality control and final testing. Before the final handover, each module undergoes rigorous quality control testing. Structural stability, airtightness, and energy efficiency are carefully evaluated to ensure compliance with Swiss sustainability and safety standards. This quality assurance process guarantees that the final product meets the highest performance standards. By leveraging prefabrication, digital modeling, and sustainable materials, Rangli Model House Vision offers an innovative, cost-effective, and environmentally friendly solution for modern housing. This modular construction method ensures flexibility, durability, and energy efficiency, making it an ideal choice for both residential and commercial applications.